Welcome to our help video, 6C10, the valence shell electron pair repulsion theory. We are on part 3 of this quiz, and we will be working with the CF2S. Sometimes it's written CSF2, sometimes it's written F2CS, different ways of writing the formula. And it also goes by different names, depending on which naming system you are using. So all these names do apply to this one molecule, depending on which naming system you're working under. But we have two fluorines on this molecule. Fluorines in family Roman 7 valence electrons, 2 times 7 is 14. We have a sulfur. Sulfur's in Roman 6 valence electrons. And we have a carbon, Roman 4 valence electrons. In picking our central atom for the molecule, carbon needs 4 more bonds to get 8. Sulfur only needs 2 bonds to get 8. Fluorine only needs 1. So carbon will be our central atom. We will put carbon in the middle and surround it with 8. So here's carbon. We surrounded it with 8. Let's attach the others. Maybe we put a fluorine right here. Perhaps we put a fluorine right over here. And maybe we go with sulfur right there on the top. Now we're going to need to surround these with 8 as well. So we've surrounded our terminal atoms with 8. So sulfur has 8, fluorine has 8. This fluorine has 8, that's 24, but here's 25, 26. We have too many electrons on this diagram as we are only allowed to have 24. So what we'll do next is pick a pair to erase. We can erase any pair from any atom, provided it is attached to another atom that has a pair to put in the bond to replace the electrons that were erased. So every one of these atoms is attached to another atom that has a pair that could be put in. Because carbon's in the center, it's attached to the 3, and it has a pair that it could put in. But would we want to erase a pair from any of the fluorines? And the answer is no, because if I erase a pair from fluorine, such as this pair right here, if I get rid of those and try to move these into the bond, that would give fluorine a double bond. If we can, we want to avoid giving atoms that don't want double bonds a double bond. Sulfur's in Roman 6. Roman 6 has no problems making a double bond. So it would be no problem of us at all to erase this pair of electrons right here. And we fix it by moving a pair from an atom it's attached to, in this case the sulfur, into the bond. We created a double bond. And that replaced the 2 that I erased from carbon. So carbon now has 8 around it. These 4, 5, 6, 7, 8. The fluorine still have 8 around it. All I did was move sulfurs from up on top into the bond. It didn't lose those. Sulfur still has 8. Those 4, 5, 6, 7, 8. So we are down to 24 electrons. Our molecule is finished, and now we can replace the shared pairs with lines. For every shared pair, we put a line. So between the sulfur and the chlorine, there's 2 shared pairs. We will need 2 lines. So we now have an opportunity to analyze our molecule to determine its shape and its properties. What do we have surrounding the carbon atom? That is where we start. How many things are surrounding the carbon atom? We have sulfur atom, fluorine atom, that's 3 things. There are no lone pairs. Remember, we count atoms, not bonds. So that's 3 things. So we can go ahead and put a 3 right here in the box. And with that 3, we know the shape is trigonal or trigonal planar, so we can circle that answer, letter B. As we mentioned, there were 3 atoms and no lone pairs on carbon, our central atom. So we can put a 3 in this box and a 0 in this box. The 3, 0 takes us to which member of the trigonal planar family or trigonal planar family it is. The 3, 0 is the trigonal or trigonal planar molecular shape. We can go ahead and circle that answer. And now we can come down and do our shape formula. Our shape formula, AB3, our B is 3, E0. So with the AB3E0, we can circle our basic shape. These 3 terminal atoms are in the same plane. That's why they call it planar. There are 3 atoms in the plane, so that plane is divided into 3 sectors by those 3 atoms. So in general, the trigonal planar family, that would be a 360 degrees to get all the way around that circle of atoms. There's 3 atoms dividing it up. The angle is normally right around 120 for trigonal planar. With the trigonal planar, again, or trigonal planar, we have our AB3E0 formula, and this is our basic shape. The bond angles are usually right around 120. But that assumes that we have all the same type of atoms surrounding the central atom and the same type of bonds. So for the purposes of this class, we could say the angle would be 120, but that was purposely not asked because there are other factors that would influence the bond angles. So let's go from question 16 to our shape to question 17. Are the atoms the same surrounding the central atom? Nope, we have a sulfur and 2 fluorines. So the atoms are different. With the atoms being different, we follow the line down. That takes us to the fact that having different atoms surrounding the central atom takes us straight to the asymmetrical shape. This is important to go through the questions in this order because it's asymmetrical shape. If we just use the B and E, 3 and 0, without looking at the atoms, watch where that would take us. No lone pairs would take us down this line, and if we don't read closely, if E equals 0, it is symmetrical, but it has to have the same type of atoms. They must be the same type of atoms. They are not the same type of atoms, so it can't be symmetrical. It is asymmetrical. With it being asymmetrical, we now need to continue on and take a look at what kind of bonds there are, because if it's asymmetrical and has polar bonds, it will be a polar molecule. If it's asymmetrical and has nonpolar bonds, it will be a nonpolar molecule. So let's take a look at the bond types. We're now going to look at the bond types here. To do that, we'll look at electronegativity differences, except we know something. Fluorine's 4O. It is the highest electronegativity of all. When fluorine is attached to any other element, including oxygen, whose second highest electronegativity, oxygen's 3,5. 4O minus 3,5 would be 0.5. It's polar. So fluorine attached to anything other than another fluorine when sharing has to be polar. So we could go ahead and circle polar right down here and then figure it out to make sure we didn't make any mistake. Again, knowing fluorine's on the molecule, it will have polar bonds, which makes the molecule polar. It's the only place you can go from polar bonds to polar molecule if it's asymmetrical. All right, let's go ahead though and double check our bonds because that's what we like to do. Let's look at the electronegativity tables. We've got a carbon bonded to a sulfur, double bond, and we've got a carbon bonded to a fluorine. So we need to find out the polarities of those two bonds. As we mentioned, fluorine's 4O. The next highest is 3,5. So fluorine attached to anything, sharing anything with other than another fluorine will be polar. In this case, we're looking at a carbon. Fluorine's 4O minus carbon 2,5. Difference is 1,5. Carbon's also attached to the sulfur. Look at that bond. Carbon's 2,5, sulfur's 2,5. Difference is 0. That bond is nonpolar. So the carbon-sulfur bond, this bond right here, is nonpolar. Carbon's 2,5, sulfur's 2,5. That's 0 difference. What about the fluorine-sulfur bond? We know it has to be polar. Fluorine was 4O. Carbon's 2,5. Difference is 1.5. So these bonds right here are polar. Now in our two-dimensional drawing, it looks like this fluorine's pulling this way, this fluorine's pulling this way. They would cancel. Well, this is a two-dimensional drawing. The molecule is actually looks like this one right down here. We've got a fluorine pulling this way, a fluorine pulling this way. We don't have a fluorine pulling that way. That's a sulfur. If it was a fluorine, they would cancel. That would be an asymmetrically shaped molecule, or an asymmetrically shaped molecule. But since this is a sulfur, fluorine, fluorine, that makes it asymmetrical. Those fluorine dipoles will not cancel, and we would end up with a net dipole, making this molecule apolar molecule. In our next video, we will wrap up our final question or part of the quiz. Part 4 will be dealing with selenium hexafluoride.